My name is Emma Griffin, and welcome to Chemical Equilibrium. To begin with the topic of equilibrium, we must review the equilibrium constant. It's funny because equilibrium is not very constant. It's defined as the state when the rate of the forward reactions equals the rate of the reverse reaction. And at equilibrium, the concentrations of products and reactants are constant. This equilibrium is represented by the constant Kc. It is integral to note that Kc can only be measured when the reaction is at equilibrium. When we're calculating Kc, it is imperative to remember a few things. Firstly, changing the temperature of a reaction will also impact Kc. Also, pure solids and pure liquids, including solvents, are not included in the equilibrium expression. Kc is often written without units, but it depends on the textbook, and the reaction must be balanced with the coefficients written as the lowest possible integer values in order to get the correct value for Kc. Now another player in this equilibrium game is the equilibrium quotient, represented by the variable q. Now q is calculated the same way as Kc, so when given this equation, this is how q is calculated. Q can be used to determine the direction that a reaction is going to shift. It's like a little chemistry fortune teller. Now, what do the magnitudes or values of each of these variables mean? If the equilibrium constant is greater than 1000, then mostly product species will be present at equilibrium. If it is smaller than a 1000th, then the mostly reactant species will be present. And if Kc is between those two benchmarks, then a significant concentration of both species will be present at equilibrium. To return to the fortune teller Q, if the constant is greater than the quotient, then the reaction will proceed forwards, favoring the conversion of reactants into products. If the constant is less than the quotient, then what? You guessed it, the reaction takes a 180 proceeding backwards, favoring the conversion of products to reactants. If they are equal, equilibrium. Now, one thing that's important about understanding equilibrium is Le Chatelier's principle. And though it sounds like a silly French guy who made a chemistry rule that we follow for some reason, that's actually exactly what it is. He basically found out that if a certain stress is placed on a system, it will cause a shift in reaction to the right or to the left, kind of like a seesaw. If a stress, like an increase in temperature, is put on a system, the reaction will shift away from the heat so that the exothermic reaction is favored. Similar to the seesaw, if two people are on it and an extra person goes onto the left side, the right side will go up. The three important factors to consider in Le Chatelier's principle are concentration, temperature, and pressure. An increase in concentration results in the equilibrium shifting away from the substance, and the same goes for temperature with the increase in heat. A decrease will cause the equilibrium to shift towards the substance or heat. And now an increase in concentration, if it results in a change of the stoichiometric coefficient, that causes the reactant to be raised to the power of the factor when calculating Kc, or the product to be raised to the factor. So this means if you are calculating Kc with 2 moles of oxygen, let's say, and in a following reaction it changes the concentration to 4 moles of oxygen, you will need to raise the concentration of oxygen from the power of 2 to the power of 4. That's really the only difference in concentration. And now in the case of pressure, an increase will result in the shift towards fewer moles, and the decrease pushes equilibrium towards more moles. And there's actually a different equilibrium constant expression, and it is expressed with Kp, and it is noted down below. Knowing what we do about Kc and Q, that rhymed, let's evaluate the reaction between sulfur dioxide and oxygen, resulting in the production of sulfur trioxide. For this equation, we are to assume that temperature and pressure are constant. Now, beginning with these concentrations, let's calculate Kc to determine whether the products or reactants are mostly present at equilibrium. I'll give you a second to take your calculators out and determine the equilibrium constant. Now, since we have found that Kc is between 1000th and 1000, what can be assumed? That's right, there are significant concentrations of both reactant and product species at equilibrium. Now we are going to measure different concentrations of the same reaction, assuming that the temperature and pressure remain the same. With these concentrations, let's set up our formula to calculate Q, using the concentrations above. I'll give you a moment to make the final calculation. Feel free to pause. Yay, the result is the same as Kc, even though different concentrations were present. And since Kc is equivalent to Q, this means that the newer reaction is also at equilibrium. Now, I know what you're thinking. Emma, you sound super passionate about this, but when am I going to need to use this? Well, you yourself may not need to use it in the future, but your body uses equilibrium every single day. The constant uptake and release of oxygen to and from parts of the body is completely reliant on chemical equilibrium. And without it, the changes in oxygen's partial pressure, facilitating gas exchange, the oxygen could not transfer from alveoli in the lungs to the blood and from the blood to the rest of the body. They couldn't do that without chemical equilibrium and your body having an understanding of how things ebb and flow. Now, this is just a quick calculation of blood O2 and hemoglobin concentration that I did to use in the next slide. Now, everybody, we're going to take what we've learned over the last couple of slides and we're going to apply it to figuring out what the equilibrium constant of oxyhemoglobin is going to be. So with this equation, how is our Kc equation going to be set up? Exactly. And then we're going to take the values we got in the last slide, plug them in right there, and I'll give you a moment to take out your calculators, get that all together. There's our value of Kc. And now what does this mean? That is correct, that mostly the products will be present at equilibrium. Good work, everybody. Now we're going to look at a little visual. Now this oxygen dissociation curve shows the equilibrium of both oxygenated hemoglobin and hemoglobin at many different partial pressures of oxygen and outlines this relationship. Now you can see from the rightward side of the graph that when oxygen has a high partial pressure, hemoglobin attaches to it, creating oxyhemoglobin, as we know from the previous equation. This causes a right-way equilibrium shift, since increasing the reactant causes the whole system to shift to the product side, and oxygenated hemoglobin reaches a harmonious equilibrium. Now, in the body, hemoglobin is used by erythrocytes, or red blood cells, to transport oxygen. So when a red blood cell travels to oxygen-deprived tissues, oxygen partial pressure decreases, resulting in the release of the oxygen by oxygenated hemoglobin, forming pure hemoglobin and allowing the oxygen to be released to the places in the body that are lacking it. Now, this release engenders a left-way equilibrium shift because of the decrease in reactant concentrations, which makes the system accommodate to replace the oxygen. In this real-world example, Le Chatelier's principles are applied to increase oxygenated hemoglobin and transport oxygen to lacking areas. Referencing back to the graph, it can be concluded that approaching 85%, equilibrium is re-established as the partial pressure no longer impacts the shape of the curve. What we're going to do is we're going to time travel to 2024. It's almost graduation, COVID has become an endemic, and you and your vaccinated friends decide to go on a vacation to Bora Bora. You could walk there or you could swim there, but the most efficient option would be to take a plane. Your friend Mary is worried because she always gets lightheaded on planes, but with your thorough understanding of equilibrium, you explain to her why this is. Picture this. You're taking off the runway, and as the plane ascends to a significant level above the sea, oxygen levels begin to drop. You know that this drop in oxygen relates back to Le Chatelier's principle. Now, since there is a decrease in the partial pressure of oxygen, equilibrium shifts to the left, which results in a lack of oxygenated hemoglobin. Since oxygen is not being delivered to tissues at its regular rate, your brain is deprived of oxygen, causing you to feel lightheaded. If the partial pressure of oxygen in the cabin becomes very low, fun little masks drop down and you and everyone else introduces new oxygen into their system. This influx of oxygen results in the aforementioned rightward shift of equilibrium, restarting regular production of oxyhemoglobin and output of CO2, allowing adequate amounts of oxygen to be delivered to the body once again. After your adventure to Bora Bora, you decide to check another activity off of your bucket list and run a marathon. Before doing this, you check out how your body will be responding to the exercise and how equilibrium can be maintained. While you're running this marathon, your respiratory rate and heart rate are going to increase. Your working muscles are moving, generating heat and creating a need for more oxygen. And according to Le Chatelier's principle, there will be a shift in equilibrium, resulting in a decrease in oxyhemoglobin concentration. The heightened requirement for oxygen, coupled with the increase in temperature, shifts the reaction to the left. Runners will have a lower hemoglobin level by about 10 grams per liter, meaning that the Kc value would be altered, but equilibrium is able to be restored with time and rest. Thank you very much for watching this tutorial, and I hope that during it you've learned a little bit more about chemical equilibrium. I hope that you're able to understand how equilibrium constants Kc and Q can be used to determine which way equilibrium will shift and whether it'll be mostly products or reactants present at equilibrium, or a good mix of the two. I also hope that you've learned how chemical equilibrium can be applied to real-world examples, like our bodies maintaining homeostasis, whether that be on a plane, running a marathon, or simply in day-to-day life. Thank you very much for watching. And here are my references. Yay!